Thank you, the organizers, for inviting me. Vienna is one of the best cities for me. I always enjoy being here, especially in this institute. I've been here many times, and every single time I enjoyed very much. Okay, so I want to talk about it goes back to 70s. So we're going to go back to 70s and see what people were doing in the 70s. If after this talk, you'll feel like 78 was a crucial year in set theory, yeah, because all of oh, I see. So which one? Oh, I see this way. Okay, so this is the standard stuff. Reals code hereditarily countable sets. Just to remind you, any hereditarily countable set can be coded this way by or some other ways that you would like by a real. Okay, so code prime is a co-analytic set. It's not analytic, as you know, but the remarkable point is, which is really the beginning of this. These days by descriptive set theory, people mean something else, but I'm thinking of cabal volumes. And this theorem sits at the very bottom of that work, yeah? So this is where scales come from and all of that. Okay, so it's a Borel. To say that two reals code the same set, that's Borel because you fix the real. Okay, so I don't want to tell you how you get to code ordinals, but because probably we all seen this before, yeah? Okay, so now we want to code ordinals by reals. Okay, so here's what happens. If you give me an ordinal less than omega 1, I can look at all the reals that code that ordinal. Yeah, and that's a Borel set. Because I can fix the one code and then define the entire set in a Borel way, in delta 1 way. Okay, so the sequence that you get is a length omega 1 sequence, and it consists of Borel sets. Right? So what we've done is we created an omega 1 sequence of sets, or Borel sets, and the members of the sequence are different. Okay, so then we have two ways of proceeding from that point, right? We could start asking questions. Are there longer sequences of Borel sets? You can ask, can they all come from the same Borel class? You can ask about how the higher level of definability, or you can do the second thing, which is just go and look Harrington's work. Okay, so what did Harrington do? Harrington, in 1978, proved this theorem, which says that if you assume pi/1 determinacy, then you'll get that every real has a sharp. Martin, of course, proved the other direction, so it's equivalence. Pi/1 determinacy is equivalent to every set having a real sharp. Oh, by the way, when I'm writing boldface, that means all, yeah? So the real parameters in the definition. The light phase will just be no parameters, no real parameters. When you see the dark, then that's all real parameters. So think of boldface 1 is the collection of all co-analytic sets, where by co-analytic we mean with the real parameter, yeah? Okay, so this is what he proved, but in that proof, oops, I skipped somehow. Yeah, in that proof, there was this theorem, which appears in the last page of the paper. And the theorem says if you assume AD plus DF plus DC, and look at Borel sets that you get after repeating the definition of Borel class up to alpha, right? So it's not important whether you're on the pi side, sigma side, just take all you get after alpha many steps. Then you can prove that there is no injection. You cannot inject omega 1 into that. This was used in that proof. Surprisingly, this was also used recently by Marx and Day to prove something called decomposability conjecture. It's just maybe 2 or 3 years ago. Okay, so that's the second theorem, is the starting point, which was proven in the famous one. Everyone knows the first one, but the second one is not as well known. Maybe it's forgotten. It was well known at the time, but now it's kind of forgotten. Okay, so let's say kappa is gamma reachable if there is an injection, if you can inject kappa into gamma. Yeah? Oh, by the way, I should say that this theorem is not a cardinality theorem. Yeah, each Borel class has continuum many sets in it. Right, so it's not a cardinality. You shouldn't think of this as saying omega-1 as smaller cardinality. It's talking more about algorithms, that if you have because we're in the context of AD, so it's saying that if you devise some kind of algorithm that's supposed to output Borel sets from the same class, it's not going to last omega-1 steps. That's the content of the theorem, it's not about cardinalities. Okay, so we take that point of view, given a definability class, gamma. What sort of lengths the algorithms can have? How long you can have this kind of sequences that outputting different sets. Okay, so let's just call them gamma reachable, if you can do that. Okay, so in that language, omega-1 is unreachable for each particular class, but it is reachable if you take all Borel, right? Because the first example I gave you, the sets were Borel. Okay, so let's go look at theta. Theta is it's basically the successor of the continuum, but when we don't have choice, that's how we define it. It's the soup of ordinals that you can surject the reals onto. And okay, so you can prove that in L of R, theta is OD reachable. That has a really easy proof. For each ordinal, we can find a surjection of reals onto alpha, but we can demand that the surjection itself is ordinal definable. And we can do that because every set is ordinal definable from a real. And then you have to think a little bit how to remove that real from it, which you can do by just looking at that definition and forgetting the real, kind of, yeah? So this is a standard coding fact. You can think about it if you want. Okay, so we have theta is OD reachable, but you can prove the Harrington counterpart. Okay, so what would be, remember the Harrington type theorem would be, you have the whole class, and then you have a stratification of that. And then you prove that there is no way of injecting into the particular class. Yeah. So here the stratification are you can stratify other ways, it doesn't matter. But one stratification is the wedge hierarchy. So you have AD plus ZF plus DC. By the way, DC is irrelevant because AD in L of R implies DC. I just copy pasted, so it's always there. Okay, so basically you cannot inject theta into a particular class of wedge degrees. Right, so the proof is basically AD implies that each particular wedge class you can surject reals onto each particular wedge class. And then from there you can deduce by a few more steps. Yeah. Okay. If you assume ADR, then you can actually prove that you cannot inject F into a power set of reals. That's not possible. With the additional hypothesis that B equals L of P of R. That reduces to the fact that every set in V is now ordinal definable from a set of reals. If you could do something like that, then that function would be ordinal definable from a set of reals, and then you'll have all the values of that function ordinal definable from that particular set of reals. And that would lead to, that would give you trouble. The AD plus is used there for reasons I don't want to get into. But you can do that. Okay, so that's theta. Here's an easy way of proving that alpha is
like this theorem of Harrington, if we replace
the real theorem?
Yeah, take theta with the correspondence of yeah. So there is there should be some theta alpha, both at less one that can be injected, right? what's the, is there is kind of refined way to say how long can we go
with
in terms of the, or, so we cannot inject theta, but can we say how, like, how far out in ordinals can we go and inject into wedge alpha?
yeah, so that's the question. I'm going to get into that question of the projected method. But that is, we will get into that. But for the projected one, then there will be some conjecture. Okay. What am I doing? I'm doing that. Okay. Okay, so this is an easy way of proving that gamma is kappa reachable. Right? You have some surjection onto kappa such that each section is in gamma. That's what we did with the reals. With reals in omega 1. And then, of course, this gives you kappa is gamma reachable, but you get more. Yeah, it's proper increase there. The sets are increasing. Probably increasing. Okay, so if kappa is not gamma reachable by these kind of sequences, then you get kappa is inaccessible. There's some CFC stuff there. This is probably not that interesting. This one is more interesting. Suppose you have a thin equivalence relation. A thin means you don't have perfect set of thin equivalent elements. Okay, so there is a theorem of Wooden which generalizes Harrington's theorem of I12. Okay, so assume AD plus ZF plus DC. You can just assume AD plus if you want to proof works from AD plus. And the theorem says that if you have a thin equivalence relation, then you can well order these classes. Okay, but what are the classes that disjoint? Yeah. Okay, so suppose you have gamma in E point class, and kappa is gamma unreachable, and then you have a thin equivalence relation such that each class belongs to gamma. Right? So you can well order the classes. Okay, it cannot well order length kappa because you have a kappa sequence of distinct sets of gamma, so it does distinct kappa. All right, so now because you can ask, okay, given an equivalence relation, how many classes does it have? The thin equivalence relation. So that's one application. Okay, so that's I want to define these ordinals, delta gamma, which are the, I don't know how to. Okay, so gamma is just a point class, but this group set theory they used to call this gamma like a point class. Gamma T is supposed to be gamma dual. I didn't know how to write. It's supposed to be written. Supposed to be gamma smile on the top, but I didn't know how to do that. So anyway, gamma T is what usually called gamma dual. It's just this collection of the complements sets in gamma, and the delta portion is the things that are in both. So think of delta 1, 1. Yeah, you have analytic, co-analytic, their intersection is Borel. But when you do logic, you get sigma 1, 1, pi 1, 1, their intersection is delta 1, 1, which is Borel. Right? So this is the logician's interpretation of that same picture, sigma 1, pi 1, 1. Okay, delta sub gamma is the soup of trivial orderings that come from delta gamma. So you're looking at the sort of the least ordinal on which you cannot subject reals to in a delta gamma way. Right? So the trivial ordering itself is delta gamma. And then there are these projective ordinals. Delta 1n is delta boldface delta 1n. And okay, so this was calculating these ordinals if you go back in the Cabal volumes, you'll see that they were trying to calculate what these deltas are. And it's pretty easy to show that delta 1, 1 is omega 1. It's, I guess, not that easy, but you can still do it. The delta 1, 2 is omega 2. Then if you do more work, you'll get delta 1, 3 is Aleph omega plus 1. Then there was a big open problem what delta 1, 5 is, and that was resolved by Jackson. Jackson actually computed all of them, all the deltas. formula, he has a particular recursive formula that gives you all the values. Okay, so it's not going to be important exactly what they are, but that's what they are, the first ones. I should say that I forgot to write it. Delta 1, 2, delta 1, 4 is the successor of delta 1, 2n plus 2 is always the successor of delta 1, 2n plus 3. So delta 1, 4 is Aleph omega plus 2. Okay, so Jackson computed all of them. What?
Why are there a superscript all along?
Because I'm going to use that later on. Yeah, it doesn't matter whether it's in D or L, but it is also L1. By calling them, they have the same. B and L have the same. Whatever that. So you don't need to write L of R there. It's delta 1, 5 is equal to that. But there is a theorem in descriptors called Mascox's coding lemma, which would show that L of R computes these guys the same way as the units. Okay, so the Kechris 78. Remember, Harrington was also 78. So he read that paper and then he did this. Or maybe they just were talking. I don't know. The story is that at that time, a lot of theorems were proven when Kechris was driving from Santa Monica to Pasadena. That's what I heard. So maybe this was one of them. Okay, so you assume AD plus DF plus DC, then you prove delta 1, 2, plus 3 is delta 1, 2, plus 1 unreachable. And so that's the gap there. You would like to do delta 1 and plus 2. In that same place, Kechris proved something extremely strange, that the union of arbitrary length of sigma 1, 2n plus 2 sets. So arbitrary length of sigma 1, 2 sets, the union of them is sigma 1, 2. Okay, so that sounds fishy because maybe, yeah, that's what he proved there. Maybe that's what motivated him to do these conjectures. The first one says delta 1, 2n plus 2 is delta 1, 2n plus 2 unreachable, right? So if you're not familiar with these deltas, look at down below. Yeah, take n equals 0, then and then delta 1, 2. Think of delta 1, 2 as omega 2. That was the first one. The second one is stronger. Of course, if you prove second one, you'll prove the first one. Okay, and then the second one was in Kanamori's book too. Okay, so then now that's 78. Now we go 90s. Okay, in the 90s, Jackson proved delta 1, 2n plus 2 is delta 1, 2n plus 2 unreachable, which was the first conjecture. And Jackson and Martin showed this is actually, I think they showed earlier than that, but Jackson then found a mistake in the proof and he reproved it in the 90s. He basically proved Kechris' second conjecture for increasing sequences and decreasing. And this theorem is useful in calculations of deltas. So there's an application for this theorem. And the proofs use the main thing they use is this partition property, but the partition property comes from the Jackson analysis, the one which he used to calculate the deltas. Yeah. So there's a very sophisticated calculation of exactly what kind of ultrafilters exist on these deltas. And yeah, we have to do that if you want to. Yeah, anyway, so he used it. And then around 90s, a different inner model theory was, and descriptive set, there were connections being developed between inner model theory and descriptive set theory. For example, Sandra talked about derived model theorem, and something called HUD analysis came up where John Steele, before that, you could prove that, for example, the first measurable cardinal in HUD is omega 1, and then the question was, what are the other cardinals? And John Steele had this idea that you take a mouse and look at the directed system given by it, then it will converge to HUD. And he used that method to prove that below theta, all regular cardinals are measurable. So there was, at that time, this is around 90s, 95, between 90 to 95, there were deep connections between the Cabal descriptive set theory and inner model theory. And Hjorth used inner model theory to prove this. So this says that Kechris' second conjecture is true for n equals 0. Yeah, and as a corollary, you get that if you have a thin sigma 1,2 equivalence relation, boldface sigma 1,2. Yeah, then it has less than omega 2 equivalence classes. Now the theorem is in V. You just assume AD holds in L of R, right? And the omega 2 of L of R might be omega 2, the true omega 2, but it could also be smaller. So in fact, I could have just written omega 2 there. Okay, and so Hjorth uses a reflection argument, which, you know, if I just, it will take me forever to just set up the context. Yeah, so for those who were asking for the proof, I can give you during the break. It's some kind of sophisticated reflection argument, but he used okay, so he used different method, but he used what's known Kechris-Martin theorem, and then it was not clear how to extend it, how to prove the full conjecture. But you can actually remove that. You can prove that the full conjecture. Delta 1 to n plus 2 is sigma 1 to n plus 2 unreachable.
Yeah.
What?
You say it's with Hjorth and from last year.
Oh, yeah. Okay, so the story is that when I was a postdoc at UCLA, Greg really wanted us to work on this. And we had some ideas, but then he passed away. So, I mean, some of the ideas come from that. I thought it's not possible because I was constantly getting stuck at extending Kechris-Martin, but he was trying to do some things. I mean, we talked a few times, but then there was that Overvolfa conference. I don't know if you guys were there. And he died. When I went back to UCLA, he was no longer there. Anyway, so I forgot about the project. And then last year I was teaching a course in descriptive set theory. I remembered it. But I mean, the proof is just taking Greg's idea and making it work without Kechris-Martin. Okay, so I cannot prove Kechris-Martin. Okay, so you get that application which I stated before. In particular, you get that sigma 1 for equivalence relations. If they're thin, they have less than Aleph omega plus 2 equivalence classes. Okay. I don't know if anyone. Okay, so maybe I go on, yeah? Okay, so there is a global conjecture, because Omar was asking, can you say globally what's happening? These kind of theorems, is delta 1 to n plus 2s and etc. So what is delta 1 to n plus 2? It's the successor of delta 1 to n plus 1. Delta 1 to n plus 1 is a Suslin cardinal. And so the natural conjecture would be to do this. What is a Suslin cardinal? You have a set of reals. It's kappa Suslin. Sandra already defined that. If you can find some descriptive set theories tree, so it's a finite sequences from omega cos kappa closed on the initial segments. And then A is the projection of the tree. Yeah. And then you say A is kappa, cardinal is kappa Suslin. If some set is kappa Suslin, but it's not lambda Suslin for any lambda less than kappa. Okay, so the conjecture would be if you have a regular Suslin cardinal, all of these odd projective ordinals, even the even ones, are regular. Yeah. So delta could have been delta 1 to n plus 1. And then you have all the Suslin sets. So if you just take the theorem that I just stated, sigma 1 to n plus 2 is the collection of all delta 1 to n plus 1 Suslin sets. Right? So it's exactly that setup. And then you want to prove that delta plus is not gamma reachable. Okay, a student at UCLA just recently verified this conjecture for delta to 1, which is the large, in L of R, that's the largest Suslin cardinal, which corresponds to the class sigma 2. 2 is on the top. Right? Okay. Okay, so there's some progress, and he's working on proving it for inductive like point classes. Okay, so what are these Kechris-Martin theorems? These are again 78. Going back to 78, and these are truly amazing, beautiful theorems. They basically say, well, that's exactly what they say. If you have a subset of omega n plus 1, which is sigma 1, 3 in codes are sharps, which is bounded below omega n plus 1, then you can pick a bound in a delta 1, 3 way. So you can say some delta 1, 3 way that the set is a subset of this ordinal. We don't have delta 1, 3, the bound. Yeah, you don't want to take a code of omega n plus 1. It's some ordinal below delta 1, omega n plus 1. Okay, so this is what it says, and it has tons of applications. For example, pi 1, 3, every non-empty pi 1, 3 set of ordinals below. So think of, you can, when you have a coding of ordinals below some cardinal, then you can talk about subsets of that, of certain complexity by just looking at how complicated the code set is. So you can prove that any pi 1, 3 set of ordinals non-empty has a delta 1, 3 member. You can then prove that pi 1, 3 is closed on the existential quantification below Aleph sub omega. That gives you pi 1, 3 is closed on the less than delta 1, 3 unions. That should be boldface. Oh, it is boldface. And basically exactly this picture is open. Not quite sure if it's open because Jackson has been saying he knows how to do it, but his techniques don't seem to be applicable in the kind of problems that I was considering. So it's definitely open in a way that I can use. So basically what the problem is, there is a coding that goes on in here, yeah? You want to say sigma 1, 3 set, that means you look at, you have some coding of ordinals below Aleph omega that you have in mind. And so you need this kind of theorem for nice codes if you want it to be useful. Whatever that means. Okay, so that's that. And this conjecture which Jackson has is basically a nice way of saying to prove Kechris-Martin style theorems for arbitrary point class. Okay. Okay, so there are other kinds of things that Greg's method gives you. This is a theorem from 1980s, not too far from 78. Okay, so if you have a set of reals A, which is light phase delta 1, 1, does it show that it's light phase? Yeah, so the delta is light phase, the pi, which is the Borel class, pi Borel class, yeah, is boldface. So that means to define A in the pi 0 alpha way, you're using some real, but you don't know what real. What the theorem says is that that real itself is nice. Yeah. Okay, so and Greg, by the same proof as his theorem that I stated earlier, is that a question or just? Okay, sorry. So if you assume projective determinacy, then you can basically lift that theorem one level up. If you have a delta 1, 3 set and a boldface sigma 1, 2 set, then there is a real in delta 1, 3, which gives you the set. And so you could try, that this is just projects for graduate students. You could try basically that with the theorem I stated for a higher projective levels. It's basically the same proof, but no one looked at it. I didn't look at it too. I just think it can be done. And then here's another one. So this would be, so what exactly we want to do? We want to prove that delta 1, by the same proof that we had that omega 1 is reachable, Borel reachable. Yeah, so you map reals onto what ordinals, look at what X codes. Yeah, so X goes to the ordinal that it codes. You can apply the same kind of proof because there is a way of mapping reals onto delta 1, 3, which is whose sections are delta 1, 3. Yeah. There is a way of getting You can find, yeah, there is a map onto this ordinal such that the sections is delta 1, 3, boldface for alpha less than delta 1. You can do that by looking at scales, yeah, for privileged orderings. And so you get that the ordinal delta 1, 3 is point class delta 1, 3 reachable, but I don't know if there is a way of doing it, this stratification. If there is a Harrington type theorem here. And I think it's a good project for graduate students, if anyone likes. Okay, I'll stop. Exactly.